When we start to analyze circuits, there's two types of circuits that we can deal with, series circuits and parallel circuits. A series circuit looks something like this when we have multiple resistors. So there's our symbol for a battery, with the positive end being the longer one. And then there's a resistor, and another resistor, and maybe three resistors, and then completing our circuit. So this is an example of a series circuit. This would be resistors in series. And a series circuit, what we notice is that each end of the resistor is attached to only one other point. So it just kind of continues in one straight line. As opposed to when we have a parallel circuit, so there's our battery, maybe with three resistors would look something like this. So when we have resistors in parallel, we get something more along these lines where each end of the resistor is connected to the two ends of the other. And the resistors are going to behave differently, work together differently in each different case. So we have to be able to identify a series circuit versus a parallel circuit to see what the difference is in how those resistors are going to behave. So when we have resistors in series, let's go ahead and draw a simple circuit here and put some numbers to it. Let's say our battery here is a 1.5 volt battery, and maybe a 1 ohm resistor, a 2 ohm, and a 3 ohm, something along those lines. When we have resistors in series, we're going to say maybe our current flows this direction. We want to look at what's happening at each individual resistor. So if we think about Ohm's law, right, V equals I R, we can figure out sort of what's happening at each resistor. First thing we have to know is that as current flows through resistors in series, this current, so a characteristic of resistors in series is that current is constant at each resistor. And so what's going to happen is at each resistor, we're going to have sort of differences in voltage based on the resistance. So the voltage across each resistor, we're going to say, actually has a voltage drop. But in order to analyze each one, what we would need is to figure out what current is flowing through this wire using Ohm's law. Well, to do that, what we need is sort of a total resistance. In a series circuit, we can find total resistance simply by adding up all of our resistors. So the total resistance in this, and right, we could have more than 3. Total resistance in this would be 1 plus 2, which is 3, plus 3, which is 6 ohms. So the current flowing through here, well, we have 1.5 volts using Ohm's law. Current times 6 ohms. So the current flowing through this wire would be 0.25 amps. And then we could use that current at each individual resistor to figure out what the voltage drop at each resistor is. But we'll look at that in a little more detail later. So now let's take a look at resistors in parallel. So there's our parallel circuit, something along those lines. And let's again, our 1.5 volt battery, and 1 ohm, 2 ohms, 3 ohms for our 3 resistors there. And again, things are going to be slightly different in parallel than in series. In parallel, we talked about how the current was going to be the same through there. Well, we're going to have some current here, some sort of total current, and then at each little branch, that current is going to sort of split up and go to those 3 different resistors. So what we'll need to find, right, if we're going to use, kind of figure out what the current flowing through each is, we're going to use Ohm's law again. The other feature of parallel that's a little different is that voltage in this case is constant across each resistor. So because each resistor is connected at each end to the battery, there's a 1.5 volt difference for each resistor. The voltage is constant across each. To find our total resistance in parallel, it's 1 over R1 plus 1 over R2 plus 1 over R3. So in this case, our total resistance would be 1 over 1, which is 1, plus 1 half. So I get our ohms there, 1 over 3 ohms. So 1 plus a half plus a third. And if we put all that into a calculator, we get 1.833 ohms. Notice that's much lower than in our previous example. So by combining resistors in parallel, you get a much lower total resistance than you usually do in series. However, there are some benefits in that you're keeping a constant voltage across them. So that's kind of how you decide how you'd want to set up your circuit. So if we wanted to calculate, what that initial current is going through there so that we could find how it breaks off, in the different points in the circuit, we'd have 1.5 volts equals our current times 1.833 ohms. And that would give us a current coming out of that battery of 0.81 amps. So notice lower resistance, higher current, right? Easier for current to flow through that system, so we get a higher current than we did before. So Kirchhoff's rules are rules that are going to help us analyze circuits, especially when they get more complicated and might involve both series and parallel at the same time. So there are two rules here. The first is what's called the junction rule. And what that tells me is that the sum of current entering a junction must equal the current leaving the junction. So for example, if we have a little junction here, so I have some current, let's call it I1, flowing in that way, and then some of it's going to split off into I2 and I3. What the junction rule tells me is that I1 is going to equal I2 plus I3. So those, whatever current going into the junction, in this case I1, it has to equal the current leaving. So those kind of a conservation of charge here in a sense, in that those electrons had to go somewhere and it had to be the correct amounts of electrons going each place. His second rule is called the loop rule, and the loop rule states that the algebraic sum of charges, of changes in potential around any closed circuit path must be 0. So there's where we're kind of talking about the voltage drops in a particular loop. So if we look at, here I have resistor 1, resistor 2, resistor 3 going around, and my current's traveling around in this direction. If I start with, let's say, 1.5 volts, the voltages at each point along the way have to add up to 1.5 volts, so that as we're decreasing voltage across the way, it's equal to what we started with, so that the total sum of charges, or of our potential energy around, is 0. So I have sort of a negative 1.5 by adding all these together to match the 1.5 that I'm starting with. And so that can help us find what the voltage is at each of these points if we know the voltage we're starting with.